Hello, today I am going to discuss about the fillet weld and butt weld. Regarding fillet weld, the remaining part of the last lecture will be discussed first, then we will discuss about the butt weld. And in last lecture we have focused mainly on the joint where the load lying in the plane of joint, that means where the direct shear stress and also the torsional stress is coming into picture. After that, partly we have discussed about the joint when the load is lying perpendicular to the plane of the joint using fillet weld. Only we have discussed about the fillet weld, we have not told anything about the butt weld. So, today fillet weld as well as butt weld will be discussed, and before going to discuss about the fillet weld, we will complete the remaining part of the last lecture regarding the fillet weld when the load is lying perpendicular to the plane of the joint. Now, in the last lecture we have seen how to calculate different type of loads, means stresses for the fillet weld joint when the load is lying perpendicular to the joint, and we have seen if we provide the torsion also, then how torsional stresses is going to develop, as well as the stress due to moment because of the eccentricity of the load and the stress due to direct load. So, all these how to take care in different points, that also through one example we have discussed. Today I will go through another practical example through which will be clear much more. So, let us go through that example. One column has to carry some load of say 150 kilonewton, say P is equal to 150 kilonewton, and this eccentricity is say 150 mm. Now, this has to make welded joint, and this is the column flange we are making. Now, this has to make the welded joint here, right, throughout this depth. Now, this depth is 150 mm, and here 100 mm long weld is also provided horizontally. Here also 100 mm long weld has been made. Now, this is the size of the column is ISHB 350 at 72.4 kg per meter, and this is ISMB 350 at 52.4 kg per meter. So, question is that the column which is of size ISHB 350 at 72.4 kg per meter, and the beam means the bracket plate through which the load is coming, that is ISMB 350 at 52.4 kg per meter. This bracket is connected to the column through the fillet weld, and the length of the fillet weld is 150 mm, along with the length in y direction. Also horizontally 100 mm long fillet weld has been used. The load is 150 kilonewton, which is 150 millimeter away from the face of the column. This is the thing. Now, you have to calculate the size of fillet weld for the joint to carry 150 kilonewton load acting at a distance of 150 millimeter from the column face as shown in figure, right. So, this is the example which we will carry out. So, let us go for the solution. So, let us assume the throat thickness as t millimeter. So, first what we have to do? We have to find out the Ixx, because if we see the plan of the welding, we will see it is something like this. So, welding is done in this way. So, throughout its periphery the welding has been made. So, when we will be calculating a stress, what we have to know? We have to know the stress due to direct force and stress due to moment, bending moment. So, we have to find out the Ixx, because FB will be m by I into y. So, let us find out first Ixx. So, Ixx, if this is the x axis, Ixx of weld section will be 1 by 12. Okay, let me write down the dimension. This is 100 mm and this is given as 350 mm, and this is T, this is also T. So, this will be 1 by 12. First, if we see this vertical portion, we will see 1 by 12 into T into 350 cube, and two faces are there. So, this will be into 2. So, 1 by 12 into T into 350 cube into 2 plus the moment of inertia due to this rectangular block, this flange. Okay. So, that will be, first will be about its own area, then from this area to here, but about its own area will be how much? That will be 1 by 12 into 150 into T cube into, this will be 4 sides are there, 1 2 3 4. So, this is very less because T is very less. So, we are going to neglect this, we are making 0, we are going to neglect this portion, this plus then the AR square, that means area we know 100 into T, this is the area, and into R square means 350 by 2. So, this is for 1 and for 2 side this will be 2 and for 2 flange into 2. So, this will become Ixx will become this plus this, that means 1 by 12 into T into 350 cube into 2 because of 2 face, this is for the wave, and for flange there are area is 100 into T and R square means 350 by 2 whole square into 2 into 2 because 2 faces and 2 flange. So, 4. Remember, we have neglected this portion, as well as again another thing is we can neglect that the area of this portion we are going to calculate twice, because when we are making for wave we have considered, but the amount is so less that we are not going to deduct this much, right. We can deduct, but for sake of simplification of the calculation we are not going to deduct this, we are neglecting this. So, after this if we calculate this, we will be getting the value as Ixx will be 19,395,833 T millimeter to the power 4, 19335833 T millimeter to the power 4. So Ixx we are going to get this much value. Another thing is the total area. Total area of weld A will be equal to, first is 2 into 350 into T, this is of wave portion, and then 2 into 100 into T, this is the flange portion, into 2. If I see, this is the flange and this is the wave. Here also again we are neglecting some portion because this is the total 350. So when we are making 2 into 350 into T, we are calculating this. So when again we are calculating the area of this portion, we are adding this much. So that much is very less, T into T it will be, which is very less. So we are not going to calculate this one. We are going to neglect that one. So this will become 1100 T millimeter square. So Ixx is found. Now what we will do? Now we will find out the stresses. So horizontal stress due to bending at the extreme fiber, because the stress will develop. If I see the stress distribution over the depth of the section, we will see stress will be like this and this stress direction will be like this. So stress distribution will be like this. So maximum stress will be either at the top or at the bottom, that means at the extreme fiber. So that will be FB is equal to M by Ixx into Y max, right. So this value, if I put M by Ixx into Y max, we will get FB is equal to M is 150 into 10 cube, this is P, into E is 150, this is P into E, which is moment, by I has been calculated 19395833 T, into Y max is nothing but 350 by 2. Okay. So FB can be calculated, which is the horizontal stress due to bending. So this can be find as 203.01 by T MPa, right. So bending stress due to the eccentricity of the load, we are going to get 203.01 by T MPa, where moment has been calculated as P into E, where P is 150 kilonewton and E is 150 mm. In the question it was given. So from this we can find out the FB. Similarly, the shear stress due to vertical load can be find out. Shear stress in weld due to direct load, which can be denoted as Fs, that can be made as P by A. Now we know P is equal to 150 kilonewton and area has been calculated. Area means the total area of the welding portion, that means area of this, then area of this, right. So 150 into 10 cube by 1100 T, which is the area we have calculated earlier. So this is coming 136.36 by T, and this will be acting as a vertical, and this value will be same throughout the section. In every point this value will be same. So we are going to get Fs and Fb. The moment we are getting Fs and Fb, we know Fs is in vertical direction and FB is in horizontal direction. So, the resultant stress will be just square root of Fs square plus Fb square, right. So, we can find out as 136.36 by T whole square plus 203.01 by T whole square. So, this is Fs and this is Fb which has been calculated. This is in vertical direction downward and this is horizontal direction. So, as these are perpendicular to each other, so we are making in this way to find the resultant, and after calculating this we are going to get 244.55 by T. So, resultant stress at the extreme fiber is 244.55 by T, where the maximum stress will develop. That is to become less than the permissible stress, which is 108 MPa for the fillet weld. So, resultant stress we can find out as 108 MPa. So, making equal to these two, we can find out T as 244.55 by 108. So, this is coming 2.3 mm. So, S now we can find out S is equal to T by 0.707. So, 2.3 by 0.707. This is coming 3.2 mm. So, the size of weld is going to come as 3.2 mm to carry the load which has been given. So, now as per the codal provision, minimum size of the weld, this is 5 millimeter and we are getting 3.2 millimeter. So, let us use 5 mm size of fillet weld. That means what we are getting now, that we are getting from the calculation of the load, the size of the weld we are going to get as 3.2 mm, but the minimum size of the weld is 5 millimeter as per the codal provision. So, we cannot go beyond that. That is why we are adapting the size of weld as 5 millimeter, right. So, to carry that much load, that means 150 kilonewton load at a distance of 150 mm with the joint as shown, we need to make the weld connection with 5 millimeter size of fillet weld. Now, we will go for butt weld. Butt weld will be basically, it depends on the penetration, type of penetration, means how much penetration we are going to give. On that basis we have to find out the size of butt weld and other things. Okay. So, butt weld is used generally when the load is lying perpendicular to the plane of weld joint. That means if it shows like this. So, in that case we can design the joint as a butt weld. This type of joint, as we have seen earlier, we can join by the use of fillet weld, as well as this type of joint can be made by the use of butt weld. So, if I see in the plan, we will see the butt weld be like this, right. So, if T is the thickness of the butt weld, then the area of the butt weld will be D into T. This is basically D and this is thickness T. Okay. So, area will be basically D into T. So, for butt weld very easily we can find out the area, then stress and then the resultant stress and other things. Okay. Let us see how to make it. Now, shear stress will become P by D into T, because area is D into T. So, now the welding should be checked for combined shear and bending. As we know, because of the eccentricity of the joint, the bending as well as the direct shear will come into picture. So, we have to see whether it is okay from shear point of view and from bending point of view as well as from the combined point of view. So, we have to check the three cases. So, first let us see the shear stress. Shear stress at the weld can be calculated from this equation, that is P by D into T, where D is the depth or length of the welding area, means welding, and T is the thickness and P is the total load. Now, again if butt weld is like this, we will see the stress is developing in this way also because of bending. Okay. So, bending stress can be found from this equation M by I into Y, where I has to be calculated about this axis, x axis. Okay. So, M by I into Y means this will be either tensile or compressive, depends on the direction of the moment. Okay. So, M by I into Y, where I is 1 by 12 into BD cube. B means T, because this is T and this is D. So, 1 by 12 T into D cube, and Y means Y maximum we will calculate, this will be D by 2, because at extreme fiber the maximum stress will develop. So, for critical condition we have to consider the extreme fiber where the maximum stress is developed. So, chances of failure will be at the end at the extreme fiber. So, accordingly we will make it, right. So, we are going to get PB is equal to 6 M by T into T square. Now, the equivalent stress as per the codal provision has been given as PE is equal to root over 3 PS square plus PB square, means as per the code IS 816/1969, the equivalent stress can be written as PE equal to square root of 3 PS square plus PB square if the butt weld is subjected to both shear and bending stresses. So, for shear and bending stresses combinedly if it acts, then we have to check for the equivalent stresses also. So, first we have to check for direct stress, it should be less than 108, and again similarly PB it has to be less than 165, the bending stress, and then PE the equivalent stress. So, three cases we have to check to find out the results. Now, as per clause 7.1.4 of IS 800, the permissible value of equivalent stress is generally considered as 0.9 Fy. If Fy is 250, then it is coming 225. So, PE will become 225, less than 225 for this type of steel, IS 226/1975. So, what I told that first is the direct shear stress, it should not be more than 108, where 108 is the permissible shear stress, and the bending stress for the butt weld it is 165 MPa. So, bending stress should not be exceeding 165. Another thing is the equivalent stress for the combined effect, that should be less than 225 MPa. That means the combined stress whatever we are coming, that is square root of 3 PE square plus PB square, that should be less than 225. So, all this check has to be done, and this is given in IS 816/1969, the formula which has been specified by the code. Now, what will do the design? Design means basically the depth or length whatever you say, this you have to find out, and size. That means this depth and size. So, basic thing is depth we have to find out. So, how to find out this depth, how much depth or length we have to make weld to carry a particular load within particular eccentricity. So, this D has to be find out, as well as if D is given, again the size of the weld has to be find out. So, both the things if it is unknown, we have to assume one thing and then other things we can find out. We have to assume a parameter, generally we assume the size, then we can find out the depth, or the reverse also can be done. Say depth throughout the length of the bracket it has been welded. So in that case we can find out the size. So in either case we can make it. Now for designing the butt weld, the length can be found out from this equation, that is d is equal to root over 6m by t into pb. Where we got this equation? Basically from here we get, because we know pb is equal to 6m by td square. Now from this I can find out d is equal to this value, d is equal to square root of 6m by t into pb, where pb is the allowable bending stress in weld, which is given as 165 MPa for this type of steel, IS 226 1975. Conforming to IS 226 1975, the allowable bending stress in the weld is given as 165 MPa. So if I put this value 165 MPa, I know the value of m, which is P into E, and I know the size of weld, or I can assume the size of weld. So from this I can find out the value of D. So with this theory we have to design the butt weld. This will be clear if we go through one example. Now let us see the example. Design a butt weld to connect a 12 mm thick, this plate thickness is 12 mm thick bracket to the flange of a column as shown in the figure below. Assume that the steel conforms to IS 226 1975. That means FB will be 225, which is given here, sorry 165. So PB or FB, whatever you, that will be 165 MPa. Okay. Here the load is 80 kilonewton and eccentricity is given as 200 mm and thickness of the bracket is 12 mm. Weld thickness has been given as 10 mm. We have to find out the length of the weld, D. So D we have to find out. So it's quite easy if we go through this. So what is given? The load is given, which is 80 kilonewton. This load is given 80 kilonewton and eccentricity is given as 200 mm, which is 0.2 meter. So now moment can be find out from m is equal to P into E. So P is 80 and E is 0.2. So multiplying this we are going to get as 16 kilonewton meter. And size of weld has been given, which is 10 mm. Now we know if size of weld is this, throat thickness will be 0.707 into 10. So this is coming 7.07 millimeter. So if we assume the length of the weld as D millimeter, then I can find out the value. And if I consider the full penetration butt weld, then the permissible stress will be 165 MPa. So these are the data we have from the code and from the question. One is I know P, I know M value, I know throat thickness, I know PB. So all these things I know. So if I know all this, I can find out the value of D. So D I can find out from the equation root over 6m by T into PB. So moment is given as 16 kilonewton. So if I put 6 MP, sorry, this will be 6 into 16, 6 into 16 by this one. T is 7.07 and PB is the permissible bending stress as per the Codal provision, that is 165 Newton per millimeter square. So D can be found as 286.9 millimeter. So we can try with a length of 290 millimeter. Why we are trying? Because we do not know whether 290 millimeter will be sufficient or not, because only from the moment point of view we have calculated the length. Now direct shear is there, moment is there, so its equivalent is there. So we are not very sure that whether this will be okay or not. So we have to check this one. We are trying with a length of 290. So if we make length 290 millimeter, PS I can find out as P by D into T, which will become P is 80 into 10 cube and D is considered as 290 from the calculation and T is 7.07. So, from this I can find out from the calculation as 39.02 MPa. So, shear stress on the weld PS is coming as 39.02 MPa, right. So, shear stress we are getting which is less than 108 MPa. So, okay, right. Another check we have to do, that is PB, shear stress due to bending, that will be 6m by Td square from the equation. So, if I put the values, 6 m is 16 into 10 to the 6 and T is 7.07 and D is 290. So, from that we are going to get 161.46 MPa, which is less than 165 MPa. Allowable bending stress is 165 MPa. So, as we have increased, it was around coming around 286, as we have increased to 290 mm, that is why the value is coming little less than the 165, because we have calculated considering 165. So, now it is coming 161.46 MPa, which is less than 165 MPa. So, I can find out the shear stress due to bending PB as 161.46 MPa. Now, the resultant stress. Resultant stress as per the Codal provision, it has been given as PE is equal to root over 3 PA square plus PB square. Mind it, 3 has been multiplied with the PA square, not only PA square plus PB square, 3 PA square plus PB square. So, if we put the value of PS and PB in the equation, that is 39.02 and 161.46, then the resultant is coming 175.03 MPa. So, the resultant stress PE is coming 175.03 MPa. This is the maximum stress developing at the extreme fiber, at the extreme end. So, PE, the resultant stress we are going to get, and this has to be less than 225 MPa as per the Codal provision. So, in our calculation also we are getting the resultant stress as 175.03 MPa, which is less than 225 MPa. So, this is okay. So, the length of the butt weld, which has been considered 290, is quite okay. So, in this way we can design the butt weld, right. So, it is quite easy how to make the things by the use of butt weld. So, what new things we are getting? One thing is that PS, PB and PE. P is the equivalent stress, which has to be less than 225, and PB has to be less than 165, and from this point of view we can find out the depth, and PS has to be less than 108 MPa. Okay. So, from these three I have to check and I have to decide the length of the butt weld or the size of the butt weld. If length is given, then size; if size is given, then length. Or other way also, in some cases you may get that load carrying capacity you have to find out. In the butt weld, load carrying capacity, depth or length is given, thickness is given, you have to find out the load carrying capacity. So, in case of that also similar way we can find out. Now, let us design the previous problem, previous joint using the fillet weld. We have designed the joint, the earlier joint, which is this one, as a butt weld. Now, let us design this same using fillet weld and let us see what is the depth is coming, right. Just to compare the process with the butt weld, we are just repeating the same problem with the use of fillet weld. Okay. So, first what we will do, we have to find out the size of the weld. Here size of the weld also can be made. Earlier the size of the weld was 10 mm. Here also we are using 10 mm size of the weld, because we have to check that whether this is allowable or not. Means maximum size of the weld generally becomes plate thickness minus 1.5. Here plate thickness is given as, bracket thickness is given as 12 mm. So maximum size of the weld can be 10.5 mm. Similarly, the minimum size of the weld can be 5 mm, right. So maximum, it depends on the thickness of the plate, but minimum does not depend on the thickness of the plate, right. So from the maximum point of view, we can go up to 10.5 millimeter, and for minimum point of view 5 millimeter. So 10 millimeter size of fillet weld, if it is used, is quite okay. So using same size of the fillet weld as in case of butt weld, let us see how much depth we are going to get. So the effective throat thickness will be 0.707 into S size. So this is becoming 7.07 millimeter effective throat thickness. Now D will become, from the equation if we see, if from plan we see, this is the fillet weld is generally made in this way. In two side welded has been done. So the area and the other things will be different from the butt weld. So here we will see the area will be basically 2D into T. Here the area will be 2D into T, as earlier we have shown also. So similarly, when we are going to calculate the length of the weld, that can be found from the equation. If we see the earlier equation, we will see that is square root of 6m by 2t into Pb, right. So here 6m moment is equal to P into E, and P is given as 80 kilonewton. So P into E is 200 mm. So 6m by 2t into Pb. Allowable stress is 108 mm for fillet weld, and T is thickness, throat thickness is 7.07, and because of this 2 row, 2T has been used, right. So D finally can be calculated from this equation as 251 mm. Now we are using the length of fillet weld as 270 mm. Why not 250 or 255 or at least 260? Because we know the stress will develop, two type of stress here it will develop. One is bending stress, which is called Pb, and another is the shear stress. Shear stress will be developing same Ps, and the maximum stress at the extreme fiber will be square root of Ps square plus Pb square. So the length has been decided from Pb. If Pb is becoming around 108, then length can be decided. But if we put the same length, then the resultant of these two will become more than 108, because Pb has been considered as 108. So whatever length is coming, if we consider the same length, then the resultant will be definitely more than 108. That is why, to be in safer side, we used to increase to some percentage of the original one. So in place of 251, we are using say 270, and let us check whether the length of fillet weld whatever we have considered 270 is okay or not. So if 270 mm length of fillet weld is used, then Ps will become P by D into T into 2, because 2T is there. So Ps will be 80 into 10 cube by 270 into 707 into 2. Then the value will be coming this much by 2. Okay. So Ps we are going to get this much. Again Pb will be 6m by 2Td square. So 6m by 2Td square. So moment is P into E, 80 into 10 cube into 200. So 6 into this by 2Td square. So this is becoming 93.13. Remember, this Pb we have considered earlier as 108, then we are getting the D as 251. Now as we have increased the length up to 270, that is why the stress due to bending is coming less than 108, which is 93.13. Now the resultant stress will be square root of PS square plus PB square, which will become, after putting the values, will become this, and which is less than 108. So the length which has been considered is quite okay. So the length of the fillet weld will be 270 mm. Earlier in case of butt weld, if you remember that the length was coming 290 mm. So here we are going to get around 270 mm to carry that the same load with the same eccentricity for the same plate. So here we are just comparing the two method, means for butt weld and for fillet weld, if the same joint is going to join by the use of butt weld and by the use of fillet weld, how the depth will be varying and how the depth will be decided, that I have shown here. Now another interesting example I will go through. After that we will be, I think, will be clear about this welding joint, that is about the intermittent fillet weld. What is that? It is the analogous to the rivet joint, means basically if we see in a line that after some gap some welding has been done with some gap. So this is called intermittent fillet weld. Now with the use of intermittent fillet weld, we will see one example. Say if we consider one example, so this is one intermittent fillet weld, this is seen in the plan. That means we are making welding with a particular pitch distance. In place of riveting, we are making welding at a particular pitch distance, at a particular interval. So the calculation will be similar, right? Now this is called pitch, center to center distance of, this is called pitch. Now the example, let us solve one example. Say one column is there which has to carry the load. This is the flange. Now right, so this is 1, this is 2, 3, this is 4. Okay, so a load of 300 kilonewton has been applied at a distance from the column face as 200 millimeter, right. The bracket is 12 mm thick bracket, right. Now the design the joint as shown below using intermittent fillet weld. Design the joint. So this joint has to be designed using this intermittent fillet weld. So this will be clear if we just go through this example. If we solve this example, we will be able to clear. Now let us first assume the size of weld. Say size of fillet weld, say maybe say 8 mm. Okay. Now why 8 mm? Because this is the 12 mm. So minimum 10.5 will be, maximum 10.5 will be required. So less than that we are making say 8 mm fillet weld. Now let us see. So what we have to do? We have to, for this we have to find out the length of this is the length, and the width of individual intermittent fillet weld, that means this one, and the pitch. So pitch has to be known, this has to be known, that means if I make this is as x2, so these are unknown which has to be designed, and the size of the weld has been considered as 8 mm. Okay. So what we will do now, we know we can write N is equal to 6 m by MPR. As per the rivet joint connection, if we see when the load is perpendicular to the joint, in that case the formula which we use is N is equal to 6 m by MPR, where N is the number of rivet we use to make. Here N is equal to number of intermittent fillet weld, and M will be the total moment, and here M will be number of weld line. So here weld line is made 2, and in the plan if we see, this is the weld line. So M we are going to consider as 2. Now P is pitch of the intermittent weld. Okay, and R is the strength of each portion of the intermittent weld. Strength of each portion of intermittent weld. Okay. So what we are seeing, so pitch we have to find out, x1 we have to find out, and R is nothing but the strength of each fillet weld, means each intermittent weld. Okay. So these are we have to first decide. Now say from the codal provision, let us see what are the things we can make it. Now as per codal provision, minimum length of intermittent weld is say x1 4 into size of weld or 40 millimeter, whichever is greater. Whichever is greater. So size of weld is 8 mm. So x1 will become 4 into 8, 32 or 40. So what we will do? We will consider length as length of intermittent weld as 40 mm. So which is denoted by x1. So this is fixed now. So what we did, this x1 is 40. Now other things we have to decide. So this 40 mm length intermittent length, this is basically effective length, which is called effective length. So actual length will generally become 40 plus 2 into size of the weld. 40 plus 2 into size of the weld. So 40 plus 2 into 8. So this is coming 56. So I can write x1 as, finally x1 will be 56 mm, because when I am talking that x1 as 56 mm, that means the actual length is 56 minus 2s, that means 40 mm, right. Next we will do x2, that means clear spacing between the two adjacent intermittent. This is the x2. So x2 is clear spacing between two adjacent intermittent. So how to find out? So this also has been mentioned in the code. As per code, this clear spacing should not be greater than 16 T, where T is the thickness of the plate. Thickness of plate, and here plate thickness is 12. So 16 into 12, that means should not be greater than 192. So as per the codal provision, the clear spacing between intermittent weld should not be more than 16 T. That means 16 into the thickness of the plate, which is 12, that means it should not be more than 192 millimeter. This is one thing. Second thing is, in any case it should not be greater than 200 mm. That means if it more than 192, say 300, then we should take 200. So now with this we can assume the value of x2. Now say assume x2 value as 180 mm. Okay. So x1 plus x2 will become 180 plus x1 was 56. So this is coming 236 mm. So, x1 and x2 is nothing but the distance of pitch. So, pitch is going to become 236 mm. So, pitch is decided. Now, what we will do? Now, we will find out the strength of each portion of weld. Strength of each portion of intermittent weld, that is R, which will be required. Strength of each portion of intermittent weld, that will be is equal to R, which can be written as T. T is nothing but 0.707 into S, this is thickness, throat thickness, into allowable stress is 108, and length of the intermittent weld is 40, effective length is 40, 56 the actual length and effective length is 40. So, this will become 24.4 into 10 cube Newton, which is 24.4 kilonewton. So, the strength of each portion of intermittent weld is becoming 24.4 kilonewton. This is almost equivalent to the rivet value. What we call rivet value, that is you can say here as strength of intermittent weld of each portion. Okay. So, now the equation which we written earlier, that is 6 m by MPR, can be made now. So, 6 m is, we know the load is 300 kilonewton, and so 300 kilonewton into P into E is 200 millimeter, the eccentricity, and m is the number of lines of intermittent weld, that is 2, and pitch P has been decided as 236, and R is 24.4 kilonewton, that means into 23. So, these are the values we have put. So, from this we are getting N as 5.6. So, we can assume the number as 6. Okay. So, number of intermittent weld we are going to get as 6. So, I think step by step how we are making all the dimensions and other things you have understood. Now, the moment we are going to get the number of intermittent weld, so let us now in plan, if I see, let us make. So, in this portion 1, in this portion another one. So, this is, so 6 intermittent weld we have made. So, this is not to scale. So, 6 intermittent weld has been provided, right. Now, I know all the details, like the length is 56, actual length is 56, effective length is 40, and this clear spacing is 180, what we have considered, all are in millimeter, and the pitch is 180 plus 56, that is 236 mm, right. Now, the total length can be find out now. So, total you can say bracket height which is required for the connections, that will be, here 6 intermittent length is there. So, 6 into 56 plus clear spacing is 5. So, 5 into 180. So, this is becoming 1336 millimeter. So, thus the answer will be that the 6 numbers of intermediate fillet weld on both sides has to provide, and size of weld will be 6. So the answer is, means when it is asking to design the joint, that means we have to make the detailing of the joint in terms of the length of the intermediate weld, spacing of the intermediate weld, and the number of intermediate weld and the total height of the bracket which is be required to make the welding, right. So this is some another type of example what I have shown here. So in fact, more we will go through different type of example, we will be able to understand more deeper way. In design like classes, it is difficult because all the things are given in the code, many things. It is difficult to make interactive with the students in this way. So I am trying to make some example so that we can understand. So in short, if I say that in the eccentric connection, what we have discussed, one is that eccentric connections are basically categorized as from the load point of view. One is load perpendicular to the plane of joint, another is load lying in the plane of joint. So these are the two basic category in which we can differentiate the eccentric connections. Again, when we are going to make the connections, we have to see whether it is bolted connections or riveted connections or welded connection. That also we have to see. If it is riveted, accordingly we have to make whether bolted or welded. Again, weld connections means whether it is butt weld or fillet weld, that also we have to think and accordingly we have to design. So as per the requirement, as per the situation demands, as per the availability, we have to decide whether we will go for rivet, bolt or welded joint, and again whether fillet weld or butt weld in case of welding joint. Other things is that in case of eccentric connection, one is through bracket we may connect, another is through sheet. So there are two category, one is bracket connections, another is sheet connections. Again, in case of sheet connections, we can categorize as unstiffened sheet connections or and stiffened sheet connection. So in this way we can make it. So all these details has been discussed in last few lectures. So I hope these connections will be clear to you, because connection is very important to transfer the load from one system to another, from one member to another member safely. So unless we do the joint correctly, the whole structure will be unsafe, though the individual members are safe, but joint are unsafe because of inaccurate design. So while going for design and going for calculation, going for analysis of the joint, we have to be very careful. Again, as I told, joint may be rigid, semi-rigid or flexible. So in case of rigid or flexible, means in case of in fact rigid, it is very easy to design, but in case of semi-rigid it is quite difficult, which is beyond our scope of lecture. So with this I like to conclude today's lecture. Thank you.